Hello students, let us start our new session of chapter number 6, Work, Energy and Power. Now let us understand this collision in one dimension. So here let us first consider a complete inelastic collision in one dimension having angle theta 1 and theta 2, as we have discussed in earlier session, that would be 0. So here for that m1 v1i equal to m1 plus m2 vf, that is a momentum of conservation equation. From that vf equal to m1 upon m1 plus m2 v1i. So the loss of kinetic energy on collision we are having delta k equal to 1/2 m1 v1i square minus 1/2 m1 plus m2 vf square. So here solve this equation. So that would be 1/2 m1 vi1 square minus 1/2 m1 square upon m1 plus m2 v1i square. This is what we have substituted the equation of vf, final velocity after collision. So that would be the result of 1/2 m1 v1i square into 1 minus m1 upon m1 plus m2. So 1/2 m1 m2 divided by m1 plus m2 v1i square. Now this is what we have discussed for the inelastic collision, that we are getting equation delta k, the loss in kinetic energy after the collision, that is 1/2 m1 f2 upon m1 plus m2 v1i square. Now let us consider this collision for elastic collision. So here theta 1 equal to theta 2 equal to 0, and momentum and kinetic energy conservation equations we are having m1 v1i equal to m1 v1f plus m2 v2f, and m1 v1i square equal to m1 v1f square plus m2 v2f square. So here m1 v1i into v2f minus v1i equal to m1 v1f v2f minus v1f, that we can get it from above two equation. So v2f into v1i minus v1f equal to v1i square minus v1f square. So that would be equal to v1i minus v1f into v1i plus v1f. So that would be cancel out from both the side, v1i minus v1f. So we are having v2f equal to v1i plus v1f. Now substituting this equation of v2f in the first 6.24 equation, so we will make the subjective formula of v1f, and we will get v1f equal to m1 minus m2 divided by m1 plus m2 into v1i, and v2f equal to 2 m1 v1i divided by m1 plus m2. So here this v1f and v2f we are going to obtain from the known values m1, m2 and v1i. So here let us take two cases. If two masses having the equal value, so v1f equal to 0 and v2f equal to v1i. So the first mass comes to the rest and pushes off the second mass with its initial speed on collision. And if one mass dominates, that m2 greater than m1, then v1f is nearly equal to minus v1i and v2f nearly equal to 0. So here the heavier mass is undisturbed while the lighter mass reverses its velocity. So if initial velocity and final velocity of both bodies are along the straight line, then it is called one-dimensional collision or head-on collision. In the case of small spherical bodies, this is possible if direction of travel of body 1 passes through the center of body 2, which is at the rest condition. So the collision in two-dimensional, where the initial velocities and final velocities lie in a plane. Now let us go through the example. Slowing down of neutrons in a nuclear reactor. A neutron of high speed, that is about 10 raised to 7 meter per second, must be slowed down to 10 raised to 3 meter per second, so that it can have a high probability of interacting with isotope, that is 235 to 92 uranium, and causing it to fission, so that a neutron can lose most of its kinetic energy in an elastic collision with a light nuclei like deuterium or carbon, which has a mass of only a few times of the neutron mass. The material making up the light nuclei, usually heavy water D2O or graphite, is called a moderator. So here the initial kinetic energy of the neutron, that is the K1I, that is 1/2 m1 v1I square, and final kinetic energy, that is the K1F, equal to 1/2 m1 v1F square. That would be equivalent to 1/2 m1 into m1 minus m2 divided by m1 plus m2 square v1I square. So loss of kinetic energy by taking the ratio of final kinetic energy to initial kinetic energy, K1F by K1I equal to m1 minus m2 divided by m1 plus m2 square. So here the fractional kinetic energy can gain by the moderating nuclei K2F by K1I. So F2 equal to 1 minus F1 for the elastic collision. That would be 4m1 m2 divided by m1 plus m2 square. Here deuterium m2, that is equal to twice m1. So that's why we are having F1 equal to 1 by 9 and F2 equal to 8 by 9. So 90% of the neutrons energy transferred to deuterium, and for carbon F1 equal to 71.6% and F2 is 28.4%. So this number is smaller than the head-on collision, which are rare. Now let us go through the collision in two dimensions. So whatever the earlier diagram we have defined, that during the collision m1 is moving with the initial velocity vi and m2 is the stationary. Then after collision they both are moving in different direction. So in this case linear momentum is conserved during the collision. So this momentum is a vector which implies in three equations for three dimension x, y and z. Consider the plane determined by the final velocity direction m1 and m2 and choose it to be the xy plane. So conservation of z component of linear momentum implies that the entire collision in xy direction. So in x and y component of that equation we are having m1 v1I equal to m1 v1f cos theta 1 plus m2 v2f cos theta 2, and that would be another equation 0 equal to m1 v1f sin theta 1 minus m2 v2f sin theta 2, which we can obtain from that earlier diagram. Here the one knowns m1, m2 and v1I in most of the situations. So here 4 unknowns would be there, v1f, v2f, theta 1 and theta 2, and only 2 equations we are having. So here we need to assume that any one or two quantities would be known, and from that the rest of the quantities we can determine. If we are taking theta 1 and theta 2 equal to 0, then one dimensional collision equation can be defined. And further collision for elastic, for that 1/2 m1 v1 I square equal to 1/2 m1 v1 f square plus 1/2 m2 v2 f square. So here this matter is simplifies if we consider spherical masses with smooth surface and assume that collision takes place only when bodies touch to each other. This happens in the games of marbles, caroms or billiards. In our everyday world, collision takes place only when two bodies touch to each other. But consider a comet coming from far distance to the sun, an alpha particle coming towards a nucleus and going away in some direction. We have to deal with forces involving action at a distance. Such event is called a scattering. The velocities and direction in which the two particles go away depends on their initial velocities and their type of interaction between them based on their mass, shape and size. Now, regarding that, let us go through the example. Consider the collision depicted in figure 6.10. It to be between two billiards balls with equal masses m1 equal to m2. The first ball is called the cue while the second ball is called the target. The billiard player wants to sink the target ball in a corner pocket which is at an angle theta 2 equal to 37 degree. Assume that collision is elastic and that friction and rotational motion are not important. Obtain theta 1. So based on the momentum of conservation, masses are having equal value. So V1I equal to V1F plus V2F. Or we can say that V1I square equal to V1F plus V2F square. So that would be V1F square plus V2F square plus 2 V1F into V2F. So here we are having that dot V1F dot V2F can be substituted with V1F V2F into cos theta, and theta we are having, that is a theta 1 plus 37 degree. So equivalent equation we are having V1F square plus V2F square plus 2V1F V2F cos theta 1 plus 37. So here the collision is elastic and M1 equal to M2 based on the conservation of kinetic energy, that V1I square equal to V1F square plus V2F square. So by comparing that equation 6.32 and 6.33, we are having cos theta 1 plus 37 would be 0. So theta 1 plus 37 equal to 90 because cos 0 at 90 degree. So here that cos theta 1 plus 37 equal to cos 90. So theta 1 plus 37 equal to 90. So theta 1 equal to 53. So here, which proves that when two equal masses undergo a glancing elastic collision with one of them at a rest, after the collision they will move at right angles to each other. Here we are going to end this session. With that, we are going to end this chapter. Hope you understood thoroughly. Thank you.